relation between wave velocity, frequency and wavelength. Wave velocity and wavelength and frequency. So it is very simple. Wave velocity we represent by v is equal to and lambda upon t, and 1 upon t is equal to, we know it is what, frequency. So we can say lambda into n, where n is represent the frequency. And wavelength is what, lambda, and velocity is what, v. Okay, so this is the relation between wave velocity, wavelength and frequency. Now characteristics of wave equation. Wave motion. Characteristics of wave motion. There are many characteristics. Let us see one by one. First, wave is a disturbance traveling through the medium. Wave is a disturbance traveling through medium. Okay, and next is what, only energy and no particle is transferred in a wave motion. It means only energy is transmitted, particle is not transmitted. Only energy is transmitted in a wave motion. Okay, next point is what, wave velocity is constant throughout the medium. But velocity of particle is different at different position. Particle different at different position. Okay, so wave velocity is constant, but the velocity of particle different at different positions. It means what is happening in this case, I can draw a diagram, you can understand this phenomena. This is the way the velocities are going. So this is the, in this way the velocities are going, but the particle just vibrate up and down at this position. Similarly up and down. So this is the particle velocities are increasing, decreasing, but the wave velocity of propagation, wave, this is the wave velocity of propagation, and this is the particle velocity which are vibrating up and down. So it is quite understand to everyone, the wave velocity is constant, but the particle velocity is different at different position. So it means be here, what is the wave particle velocity is 0, here the particle velocities is 0. So these are the point where the particle velocities are 0. These are the point where the particle velocities are 0. These are the point. Okay, now so the next point is here, energy transfer takes place with constant speed if medium properties are homogeneous. So if medium properties are homogeneous, then energy transfer takes place with constant speed. So energy transfer takes place with constant speed. The next point, there is a continuous phase difference amongst the successive particle of the medium. This is also important point, means phase difference of every particle are different. Now these are the some characteristics of wave motion. One more important properties are also we have to discuss here is what wave motion is possible in a medium. Wave motion is possible in a medium which possess the property of elasticity and inertia. Of elasticity and inertia. Okay, so this is an important point. The wave motion is possible in a medium which possesses the property of elasticity and inertia. If anywhere, if elasticity is not, means you can conclude with these situations. If you want to find at which place the velocity is more, in case of steel, velocity is more as compared to the rubber, because the more elasticity in the steel as compared to the rubber, so velocity in the steel is more as compared to the rubber. Now come to the main topic is now these are all related to the common phenomena of the waves. Now come to the main topic is how to sound wave is correlate with this one. Sound wave. So basically sound waves, what it is also a mechanical waves, or sound waves is an mechanical waves. Why? Because it travels in the medium, that's why we say it is a mechanical. Let us see the some how we sound measure or we feel. Sound is a forms of energy which affect our sensation of hearing through the ear. The sound is a form of energy which affect our sensation of hearing through the ear. Okay, the sensation is produced by longitudinal waves in an elastic medium. Is produced by longitudinal wave in an elastic medium, where the vibration of the particle are in the same direction in which the wave propagate. It is very important because in longitudinal waves what is happening, the particles vibrate in the same direction of the propagation of the waves. So it is happening here where the vibration of particle are in the same direction in which the wave propagate. Now this all we have seen. Now we see propagation, production of sound waves. So the production of sound wave in laboratory, sound is produced by tuning fork. In laboratory, sound is produced by a tuning fork by striking its one prong on a soft rubber. This is the laboratory method. One more method, sound can also be produced by plucking a stretched string boiling by blowing flutes, by striking tabla, and many other ways. It means you can produce sound in many ways, in anywhere. If you hear the sound, this is a production of the sound by violin or by blowing the flutes and by striking on the tabla and many more. So this is the laboratory method we use in the further. So now the propagation of the sound. Next is topic heading is very important. How the sound is propagate in the medium or air. So the propagation of sound. Propagation of sound. Take a tuning fork, a source of standard frequency. It is set into the vibration and its prong A and B are kept vertical. What we have done it, you can see. I'll make a diagram for you, then you can see what is happening. This is the tuning fork. This is the tuning fork, and these two are A and B. So take a tuning fork kept vertical, the prong moves in and out their mean position, have a transverse vibratory motion. Then what we are doing is, now when the prong are in mean position, the air in their surrounding has normal density. It means this, the positions you are looking here, this is the mean positions. If without anything, so airs are looking is very stretch. It means no disturbances in the air. This is very straight. Okay. Now what will happen when the disturbances are is there in the prong? It means either this is stretched or compressed. So suppose if it is stretched, then what will happen? Suppose now the position is like this. You can see here, such that now it is stretched. Okay, so when it is stretched, what will happen? Now the position A and B shift their mean position, and now the nearby air is compressed. Now this is compressed as compared to the far side air. Okay, so this you can understand what is happening if these prongs are nearest, these prongs are stretched, then the nearby air is compressed, and when it comes again in normal positions, is like in upward positions, as we are discussing here. This is again is the mean position. Then what will happen? At this time, this disturbances moves forward. So now it moves forward, and the nearby of the prong A is again in the normal position, but this disturbances moves forward, so it may be at any time. This is here, so I am just taking the lines are near closer. It means this shows the disturbances at this place is here. So this is the disturbances which was at the initial, now it is here. So you can see the disturbances in this zone, these zones. It means some velocities are here. This is the velocities which travels this disturbances at, it was in the beginning here, now it is here. So this is very clear too. In the fourth position, if we see, now if this prong is compressed, mean this is the position of the prong. So what will happen now in this case? The rarefactions, this is known as compression. What we say, this is a compression. This one. Now what will happen when this prongs closer to each other, this A and B are closer to each other, then what will happen? The air now stretched. In the previous case it was in compressed, now it is stretched. So you can see the distance of the vertical lines are just is increases. Distance between the vertical line increases, and this disturbance is continuous, and this will move further ahead. So you can see this section is represented by rarefaction, from here to here. You can see here, because of air, this prong is A and B of the prong is near to each other. This represent the rare fraction, this represent the rare fraction, and this represent compression. So you can see waves now is generated because the rarefaction and compressor are both are traveling in the horizontal direction. Okay, with the wave velocity v. This we have discussed earlier. Now it is clear to everybody how the waves are generated and what is the concept of the rarefaction and compression. Rarefaction, where the vibrations distance between the vibrations are increases, and compression, when the vibration are compressed to itself. Okay, now this is the basic concept of the wave generations or the sound generations. Now one more thing is necessary for the sound generations. The sound waves needs a material. Without material it cannot propagate. It means in the absence of the medium, means like air around the source, sound is not being propagated. So whatever we have done it, this is in the air. So this is an important point. In the absence of the medium, means air is also around the source, sound is not being propagated. So this is a very natural phenomena of the sound. A natural fact, moon has no atmosphere. Moon has no atmosphere. Moon has no atmosphere. It means the sounds cannot be here on the moon. Okay, so these are the basic today we have seen. Let us conclude today's we have seen is the basic concept of the sound, how the sound waves are generated. Okay, thank you.